Check it.
Okay, welcome back. Today we're going to be talking about adding and subtracting square roots. Now, before you can add or subtract square roots, you have to make sure that they're fully simplified. So we're going to talk about simplifying radicals, not just square roots, cube roots, other roots as well. So simplifying radicals is what it's called. We have here a radical 300, okay? And it's a square root because there's no number here, so it's a 2. And if you just take out your calculator and do this, you'll get a decimal. And we don't want any decimals in this lesson at all. Matter of fact, any decimals in this whole chapter. And for the most part, we don't want any decimals in all of Algebra 2. So we definitely don't want to take out a calculator and do the square root of 300 and get 17.32 something. That's not what we're interested in. What we want to do is figure out how do we take this square root of 300 and break it down, okay, so that we can get the most simple version of this radical. Now, once you know how to simplify radicals, then you can add them and subtract them, but you can't do them while they're not simplified. So you have the square root of 300 here, and you can't square root it the way it is, but you can factor it. You can realize, well, you know what, this is the square root of 100 times the square root of 3, isn't it? And the square root of 100, we know this is a 10, and the square root of 3 is definitely a decimal, so we won't bother doing anything with that. And there you go, 10 radical 3. That's the square root of 300 reduced to simplest terms, okay? But how did I know that 100 was in there? Well, because it's a really easy situation here. You know, 300, obviously 100 is in there. But the numbers are usually not that simple. So what we do to make sure that we find the right numbers is we create what's called a factor tree. We take the 300, or whatever number's inside the radical, and we break it all the way down to prime numbers, okay? So here's how you do this. You take your number and you find any two numbers that will multiply to give you 300. So like 150 times 2 or 30 times 10. Let's go with 30 times 10 or 6 times 50 or something. So 30 times 10. Okay, now you do it again. What are any two numbers that will multiply to give me 30? It doesn't matter which ones you choose. 10 times 3, 5 times 6. Those are pretty much your own. I'll go with 3 times 10. Why not? And how about the 10? Can you break down the 10? Well, 5 times 2. Okay. Are these all prime numbers? Well, 3 is a prime number. You cannot factor it. There's no other factors other than 1 and 3 that give you 3. 5 is a prime number. 2 is a prime number, but 10 is not. So 10 still needs to be broken down, and 10 is 5 times 2. So now bring down this. This is a 3. Bring down this. This is a 5. And bring down this. This is a 2. This bottom row has to be all prime numbers. So I've done it. I've taken 300 and broke it down into prime factors. Okay, 3 times 5 times 2 times 5 times 2 equals 300. Now group together the like factors. So there's only one 3. There, however, are 2 5s, so 5 squared, and there are 2 2s, so 2 to the second power as well. There's 1 3. We don't really have to write the 1. 2 5s, so 5 times 5 right there, and 2 times 2. So once you do this, and you factor into primes, and the second thing is you group these into powers, you take this and you square root this instead. So we're going to square root 3 times 5 squared times 2 squared. Now it makes more sense to write this as separate radicals, so let's do that. Let's write it as the square root of 3 times the square root of 5 squared times the square root of 2 squared. Okay, in the last lesson you learned that when you have a power here, you divide the power by whatever index number is out here. Well, these are all square roots. This is a square root, so these are all square roots. They all have an invisible 2 that we don't write. That's why I wrote it in red. This is a first power right here. 1 does not divide by 2, so leave this alone. However, for this one, 2 does divide by 2, and you get a power of 5 to the first power, or just 5. Here, same thing. 2 divides by 2 gives you 1. This becomes 2 to the first power, so that's just a 2. So now you have 5 from here, 2 from here, and this square root of 3 right here, you can't do anything with it, so you leave it on the end here. Now 5 times 2 is 10. radical 3. And that's what we got before. So if you can find a perfect square like 100 times a prime number is important here, then go ahead and do that. That's a shortcut. But most of the time, you're going to want to use the factor tree because the factor tree will help you. Well, let's put it this way, it's foolproof. So no matter which way you choose your numbers, I could have chose 150 times 2 or whatever. I could have chose 6 times 5 here. It doesn't matter. Eventually, you get to the same exact prime factorization. So no matter which way you go, 300 has to be 3 times 5 squared times 2 squared. Or if you want to go 2 squared times 3 times 5 squared. It doesn't matter the order, of course, but you will get the same prime factors, and the prime factors, then you can do the square roots that way. Let's try 128. 128, when you square root it, is a decimal. Here's my advice to you. Try to square root, you have access to a calculator. Try to square root the number and see if it's a perfect square, okay? If it's a perfect square, you're done because you get a whole number answer. Remember, you're not allowed to have any decimals. However, here, 128 is a decimal. So here's what we do. We make a factor tree. 128. Find any two numbers that'll multiply to give you 128. It doesn't matter how you do it. So usually, if you can't think of anything, at least cut it in half and go 64 times 2. That's the easiest thing to do. And then 64 becomes 8 times 8, or 16 times 4, or 32 times 2. It doesn't matter. And then this one right here, this is prime already. Just bring it down. Once it's prime, just keep bringing it down. So now I got 8 times 8 times 2. And on the 8s, each one becomes 4 times 2, 4 times 2, and that one's just 2, right? And then the 4s become 2s. So 2 times 2, bring this one down. This becomes a 2 times 2, bring this one down, and that's a 2. Okay, I have now a prime factorization. Now it's just time to group into powers. This is actually all one number. It's 2 times 2 times whatever. So it's 1, 2, 3, 4, 5, 6, 7 2s. So 128, it turns out, is just 2 to the power of 7. That's the same as 128. If you take a calculator, go 2 to the 7th power, you'll get 128. So now you take that 2 to the 7th power and you square root that instead of square rooting 128. You do that. Now remember, we're doing a square root here, so there's an invisible 2 here. Divide the 7 by 2 and you'll be able to do the square root. But 7 doesn't divide by 2 evenly. And we don't want 2 to the power of, well, 7 divided by 2 is 7 over 2, which is a rational exponent, meaning a fraction power. We'll learn about that later in the chapter. And we definitely don't want a decimal like 3.5. We don't want that. So what do we do about this? Okay. Well, in a way, it's not really a factor tree, but in a way, you can kind of do like a little factor tree here. You want to break this down the same way you broke this down, that's 128, so that you have something you can square root. So what I suggest you do is come down 1 power at a time, okay? And try, okay, so 7 doesn't work. 7 doesn't divide by 2. Come down to 6. So 2 to the 6th times what would give you 2 to the 7th? Well, 2 to the 1st, right? Would this work? Yeah, it would work for 2 to the 6th. You can square root 2 to the 6th. And then the 2 to the 1st, that's just going to end up just staying the way it is, okay, as like a remainder. So here's what we're going to do here. We're going to take this 2 to the 7th power here, and we're going to break it into 2 to the 6th power and 2 to the 1st power. I'm not even going to write the 1 here, okay? Why did I do that? Because now this will divide by the invisible 2 that's here. 6 divided by 2 is 3, and this becomes 2 to the 3rd power, and this is going to be radical 2. Now, what is 2 to the 3rd power? It's 2 times 2 times 2, which is 8. So we get 8 radical 2, and that is the square root of 128 fully simplified. All right, let's try another one. This time we're not doing the square root of 128, we're doing the cube root, the 3rd root of 128. So that's a 3rd root there. Okay, last time it was a square root because there was no number here, it was a 2nd root. This time we're doing a 3rd root. Now the process is exactly the same. You're going to make a factor tree. Now we already made the factor tree for 128. We already know it's 2 to the 7th power, right? We already know it's 2 to the 7th. So we can save a little time here. 128 is 2 to the 7th power. So just take your 2 to the 7th power and take the cube root of that instead of taking the cube root of 128. Does 7 divide by 3? No. So like I said, come down 1 power at a time until you can divide by 3. So does 6 divide by 3? Yes, it does. So we'll do that. We'll break it into 2 cube roots. Remember, they have to be cube roots now. 2 to the 6th 2 to the first. I'm not going to write the first power, so I'm going to take that off there because it's unnecessary. It's redundant. Or superfluous, as it were. Now, we're going to divide 6 by 3 here and get 2. So this becomes 2 squared, right? Because 6 divided by 3 is 2, and that's the power that ends up here. And this cube root here, this is a 1, and 1 doesn't divide by 3. And you can't come down from 1 because you're already as low as you can go without going to 0. So this radical remains as it does. Like, it just stays as the cube root of 2. So what is 2 squared? It's 4, and your answer is 4 times the cube root of 2. And there you go. You just did a cube root of 128, and this up here was the square root of 128. Okay, the process is exactly the same. In both cases, you make a factor tree, you find out what 128 is when it's in prime number terms, and then just take the root of that, and it's pretty simple. Okay, now let's do the same thing, but we're going to do it with letters now. Okay, so a minute ago we had 2 to the 7th power with a third root outside, and we said 7 did not divide by 3. Well, now instead of having a 2, we have an x. We have the third root of x to the 8th power. Does 8 divide by 3? No. So like the other one, you're going to do the exact same thing. Come down 1 power at a time until you can divide by 3. Okay? Now obviously if you're starting below 3, this doesn't work. If this was a 2 or a 1, you're stuck already because you can't go any lower than that. But this is an 8. An 8 doesn't divide by 3 evenly. What about 7? No, 7 doesn't divide by 3 evenly either. What about 6? Yeah, 6 works. So this becomes x to the 6th cube root times the cube root of what? What would make this complete? Well, you need an 8 here. This is a 6. You need a 2 here, right? You have 6 plus 2 gives you 8. So there you go. You've broken it down. Now what does this become? 6 divided by 3 is 2, so this becomes x to the 2nd power. This is already lower than this, so you can't do anything with it, so just bring it down. It's already as simple as it's going to be. And there's your answer. Okay? The cube root of x to the 8th is x squared times this kind of remainder over here. That's sort of what it is. Okay. Let's do the square root of this fraction now. How do you take the square root of a fraction? You take any root of a fraction by taking the root of the top and the root of the bottom separately. So we'll take the root of 50 on top divided by the root of the bottom, like that. Okay? Now, does 50 root evenly? Is there a square root of 50? No. There's a square root of 49, but not a 50. So this is going to be 7 point something. But here's what we do. We make a factor tree for the number. So for number, just to be clear, for numbers, you need to make a factor tree. For letters, you just do what we did up here. So for numbers, we have 50 here. We want to break this down into prime factors. So 5 times 10, okay? And 5 is prime, so just bring it down. But 10 becomes 5 times 2. And now all of these are prime numbers. 5 is prime, 2 is prime. So 50 is 5 squared times 2. So instead of trying to square root 50, square root 5 squared and square root 2. Square root of 5 squared, also known as the square root of 25, when you divide 2 by 2, that becomes a 1, so you just get a 5. This, on the other hand, has a power of 1, which won't divide by 2 because it's lower, so this just remains radical 2. So this top part here is 5 radical 2. The bottom, well, you have the square root of 4 here. Sorry, not the square. You have a power of 4 here, and it's a second root. So divide the 4 by 2, and you get x squared. And you're done. There it is. Okay? So once again, for numbers, you want to do the factor tree. And for letters, you just come down 1 power at a time if necessary. In this case, you were just able to just go ahead and do it. Okay, let's do this one here. This is the cube root of a bunch of stuff. The cube root of a fraction, first of all, 2 over 27. The cube root of a to the 4th, the cube root of b to the 6th, and the cube root of c. Okay, because what I did was, like we did in the last lesson, I chopped this up into 4 roots. Now, in the last example, we did the cube root of a fraction. We just did the top and the bottom separately. So this is going to become the cube root of 2 on top and the cube root of 27 on the bottom. We'll come back to this and simplify this some more. This is a to the fourth. Does 4 divide by 3? No. So come down one power at a time. How about a to the third? Would 3 divide by 3? Yes. So we'll chop this one up here. We'll break it up into a to the third times a to the first. Okay, remember these are all cube roots. You have to write the 3. How about this one? B to the sixth. Does 6 divide by 3? Yes. You just get b squared. And this one, even though we don't write it, this is b to the first power, right? Sorry, c to the first power. And 1 doesn't divide by 3, and you can't come down because you're already lower than 3. So this just stays the way it is. This will just remain the cube root of 3. So cube root of c. Okay, so what can we simplify? This is the cube root of 2, which you can't do anything with because it's a first power here, and 1 doesn't come, you can't go down. So the cube root of 2 stays the same. But what's the cube root of 27? Well, it turns out 3 times 3 times 3 is 27, so it's just 3. That's done. How about this one? The cube root of a to the third. Well, the 3's cancel out, and you just get an a. This, on the other hand, is a to the first power, and that's not going to go anywhere, so just leave that as the cube root of a. This is already done, so bring it down. And this is not going anywhere, so bring that down. So here's our unorganized answer. Now, what can we do with this? Well, if you have radicals, you can combine all of these into a single radical, the letters at least. So the a and the c that are in cube roots, you can put them all in a single cube root. Now, radicals like this go on the far end of the expression, on the far right. So this number here, I know it has a radical in it, but we're just going to treat it like a number. So this radical, this cube root of 2 over 3, and this a and this b squared, okay, all of those go first. And then one big radical, one big cube root for all the leftover letters, so a and c. And that is your answer here. If you really want to be a stickler, I suppose, if you really want to be kind of literal, maybe I shouldn't leave this radical 2 here. In which case I could break it up and write this here, write this as the cube root of 2 times 1 over 3, right? That would be the same as that. And if that's the case, then I would have 1/3 ab squared, and I can put that cube root of 2, I could put the 2 in here, 2ac. So I guess that would be the ultimate way to do that, the final way. Okay, so the next section is going to be all about adding and subtracting radicals. Now, we said before that we're going to simplify these so that we can add and subtract them. Now we're going to actually add and subtract them. Okay, so there are a couple of really important rules that you have to keep in mind when you're adding and subtracting roots. Okay, you can only add roots that are the same root, meaning you can only add a square root to a square root. You can only add a cube root to a cube root. In this case, you can only add a fourth root to a fourth root. That's the first requirement. Same root, okay? Meaning the same index number, okay? So this has to be the same for both. And this is maybe surprising, the same number has to be inside the root for you to be able to add them. So these two requirements have to both be met. So let's take a look over here. We have a square root of 3 plus a square root of 3. They're both square roots, so they are the same kind of root. They both have a 3 inside, so they have the same inside number, same argument. So that means you can add them. Now, how many, everything has a number in front of it. If there's no number in front of it, then you assume it's a 1, right? You have 1 square root of 3 plus another square root of 3, and that's going to equal 2 square roots of 3. And there you go. How about down here? Well, look at the root. This one's a fourth root, and this one's a fourth root. So yeah, they're the same root. So far so good. Also, the number inside the root is a 2 here. The number inside the root here is also a 2. So they're both fourth roots of 2. Fourth roots of 2, fourth root of 2, fourth root of 2. So you have 10 of them here minus 7 of them here. How many fourth roots of 2 do you have? Well, 10 of these things called fourth root of 2 minus 7 of these things called fourth root of 2 is 3 of these things called the fourth root of 2. And there you go, there's your answer. Just make sure they're first of all the same type of root and the same number inside. So those first two examples kind of went smoothly because they were identical. Now you look at this third example, and if you're going strictly according to these rules, you might say can't do it. But the fact is you can do it, but you have to simplify these radicals first. You won't be able to tell by looking at a lot of problems whether or not you can add or subtract them. You can only tell after you've simplified. So let's simplify square root of 72 and the square root of 50, and then see if we can or cannot add them. But we can't tell by looking at them now, because right now it's a no. Right now they're not the same number inside, so we think we can't add them, or in this case subtract them. But no, you have to simplify these first. So let's do our factor trees. For 72, we'll break it down. 72 is what, 9 times 8, right? And this is 3 times 3, and this is 4 times 2. And then, well, 4 needs to be broken down further, right? And then bring all the other prime numbers down. So 72 is 3 times 3, which is 3 squared, times 2 times 2 times 2, which is 2 to the third power. So 72 becomes the square root of 3 squared times the square root of 2 to the third power. What about 50? Let's do a factor tree for 50. 5 times 10, that's already prime, so just bring it down. And this is 5 times 2. So 50 is 5 times 5, which is 5 squared, times 2. So that's going to be the square root of 5 squared times square root of 2. So let's keep simplifying here. The square root of 3 squared. Now these are square roots, so they have the invisible 2 that we don't write on all of these. And you can see this 2 divided by this 2 is a 1, so this just becomes a 3. Right? 3 to the 1, we don't have to write the 1. This, on the other hand, 3 is higher than 2, but it doesn't divide by it. So you can come down and break this up into 2 squared times 2 to the first. I'm not going to write the 1, but there is a 2 and a 1, 2 to the first here. And once again, this has got a 2 here. This has got a 2 here. Okay? And what's going to happen is this will become a 2, right? Because the 2 divided by 2 gives you a 1. And then 3 times this 2 will give you a 6. So this is going to be 3, oops, wrong color. This is going to be 3 times, this is going to be a 2 right here. And this radical 2 ain't going anywhere, so leave that alone. How about here? 2 divided by 2 is going to be a 1, so this just becomes a 5. So you have minus 5. Radical 2 is not going anywhere. So we now have 6, 3 times 2 is 6. Radical 2 minus 5, radical 2. Okay, when we looked at the question before, we did not see the same number inside the roots and thought we cannot subtract. But when you simplify, take a look. 6 root 2, square root of 2, minus 5 square root of 2. They actually are the same root. So you can subtract them. But you can't tell that you can subtract or add until after you've broken things down with your factor trees. Okay, you need to do this. So, what's 6 of these things called radical 2 minus 5 of these things called radical 2? Well, 6 minus 5 is 1, so you just get 1 of these things called radical 2. And that's the answer for that. Okay, let's try another one. 10 radical 2 minus radical 8. Or, and they're square roots. 10 square root of 2 minus square root of 8. Plus square root of 8. Well, at first glance, they're both the same type of root. They're both square roots. That's good. But they have different numbers inside. That's bad. You can't add those yet. Can we break these down? Well, 2. Can you break down 2? No, you can't, because 2 is a prime number. So 10 radical 2 is just already as simplified as it can possibly be. Because what's the factor tree on 2? It's 2 times 1. Okay? And you're not going anywhere with that. Okay, but 8, you can break down 8. So let's break down 8. 8 is 4 times 2, and that's 2 times 2 times 2. So 8 is actually 2 to the third power. So instead of writing this as a square root of 8, we're going to write this as a square root of 2 to the third power. Now remember, this is a second root. Does 3 divide by 2? No. However, if we just bring this down here, because this is not going to change, this can be broken down into the square root of 2 squared times the square root of 2 to the first. 2 plus 1 is 3. You don't really need to write the first power, so I'll drop that. And once again, these are the invisible little 2's that are supposed to be here. So this 2 divides by 2, and you just get this becomes a 2 right here. So we have 10 radical 2 here, plus that whole thing's a 2 radical 2. And it turns out they are the same radical. So what's 10 radical 2's plus 2 more radical 2's? It's 12 radical 2's, and there you go. It's like saying 10x plus 2x is 12x. Okay, 10 apples plus 2 apples is 12 apples, that sort of thing. Okay, All right, last one. Let's add together these, or add and subtract these radicals here. Now, at first glance, none of them match. That's a 2, that's a 27, that's a 50, that's a 48. But we can break them all down or simplify them all. 3 radical 2 is not going to simplify for the same reason that 10 radical 2 didn't simplify. 2 is a prime number. But 27, try to square root it. You can check it. Okay, you can check all of these. None of these square root evenly. Like, none of these are perfect squares, so they all give you decimals. So let's break down 27. 27 is 9 times 3, which is 3 times 3 times 3 times 3. So 27 is 3 to the third power. Now I'm going to show you a shortcut here. We could go ahead, come over here and do the square root of 3 to the third power. But did you notice that this is 9 times 3? This is a perfect square already. And this is a prime number. If that happens, you can kind of take a little shortcut and just say, all right, well, 9 times 3. Because that's going to square root perfectly right there, and that cannot be reduced. So if you see a perfect square on the way down and this number here is prime, you can just stop there and use those numbers instead. Okay, it's a little faster. Same thing with 50. I could go 5 times 10 like I did in the previous example. I intentionally avoided the shortcut. But you might say, hey, this is 25 times 2, isn't it? And that's a perfect square. So this will save you some time. You can just use these numbers. So we have here the 2 from the outside here. We also have the square root of 25 times the square root of 2. 25 and 2 right there. And 48. We could go 48 is I don't know, 8 times 6, and then 4 times 2, and there's 3 times 2, and then 2 times 2 times 2 times 3 times 2. Or you could realize 48 is 16 times 3. Once again, a perfect square times a prime. This has to be prime. If this is not prime, then there's a chance that this is not going to work the way you want it to. All right? But if you happen to get to a perfect square times a prime, you can just write 48 as 16 times 3. And there's the thing you're going to square root, and here's the remainder. Because it's prime, you know you're not going to break this down. So there's a little shortcut right there. You could do the full factor tree. It'll come out the same. But if you see the opportunity to get a perfect square like this and a prime number, then go ahead and do that. It's a little bit faster. So 3 radical 2, that's prime already. That's not going anywhere. But this right here, what's that? That's a 3. So this is going to be 3, and the radical 3 is not going anywhere. This right here, the square root of 25, that's a 5. And 5 times 2 is 10. So we get 10 radical 2. And this right here is a 4. 4 radical 3. 3 is prime, so it's not going anywhere. And now we're done simplifying. Okay? And now we look at it and go, all right, is there anything here we can add? And we can't add all of them, but we can add this with this because they are the same root. So 3 radical 2s plus 2 more, plus 10 radical 2s is 13 radical 2s. And then we also have radical 3 here and radical 3 here. 3 radical 3 minus 4 of them. So 3 of something minus 4 of something is negative 1 of that something. So we get negative 1 radical 3. But we don't have to write the 1, so it's just negative radical 3, like that. And we are done. See you at the next video.
Check this.